All right, welcome everyone. Today, yesterday actually, when I was doing trees and graphs, I kind of ran out of steam. I didn't really approach many questions. Decided to work on other stuff and for front-end interviewing like CSS grid. So I took a little break. I didn't do too many questions. And one of the reasons for that was that I really don't get asked too many trees and graph questions. And when I do, it's mainly about, hey, do a breadth first search or depth first search through this tree-based data structure that we've already made for you. Figure it out. Let me know how that goes. So that's typically the questions that I get asked. Today, we're going to go over breadth first search and depth first search. And I might cut this short at an hour. Just because I have some other stuff I want to prep with. And this one is not as frequently asked in the first place for front-end developers. If you're a back-end developer, if you're a machine learning, if you're in something else, trees might come up more often. I still find them to be my favorite data structure of all, though. And we're going to do, I'm still going to teach about graphs and how to do breadth first search and depth first search over them. You could do depth first search and breadth first search on a tree as well. Just heads up. But yeah, we're going to learn those today. So let's dive into it. I'm going to get my iPad together. So we're going to learn about graphs and about depth first search and breadth first search. First, we're going to talk about graphs. I'm going to share my iPad here. All right, almost in this whole song and dance. All right, so you'll remember from last time, a tree is basically something with this general form, right? There are nodes, there are leaves, there's children, but they never do this. They never go back and reference something outside of their tree form. As soon as they do that, they turn into a graph instead of a tree. And that's really the only big difference, is that a child node of this guy could actually end up being this node here. In fact, at that point, is it even a child, right? It's more of just a node that's connected to other nodes. And there's lots of ways of representing this. One is to have the actual graph itself. You have the node, right? So class graph node. And it obviously, maybe it has in the constructor, we could have like a value, right? And then this dot value would equal whatever is initialized to, and then this dot nodes, maybe even neighbors. So there's a whole bunch of terminology you could use there. I'm just going to use node. And then when you add a node to it, you just add it to this dot nodes, right? There's no rhyme or reason to it. You can add anything there that is a node for that to work, and you can create this graph just based on having a series of these nodes, right? So that's the basics of a graph. Now there's a little more to it. A few things to it. Sometimes graphs they point in certain directions. So you might have it to where it points in one, but not the other. What does that mean? That means maybe this node, let me use red. Maybe this node is connected to this node, but the reverse is not true. This node is not connected to that node. And that's the difference between directed and acyclic graphs. Let me get my book real quick because I forgot the difference between the two. I'm going to pause. Sorry, it was actually directed versus undirected. So undirected are the two-way street, right? And unidirected is when it's just one way. So this is one way, and this would be the two-way street, right? They're connected to each other, or rather one's connected there, the other is connected to it like that. So that's directed versus undirected. I think the other thing that is important are different ways of representing graphs. I recommend going through the book on this one You have adjacency lists, which is one particular way of doing it. The thing is that so an adjacency list, imagine this, we have 0, 1, 2, 3, 4. These are just keys in a key value pair. Or I'm sorry, these are the nodes themselves. So imagine we have this graph, 0, 1, 2, 3, and then 4. We'll have this. We'll have it like that. So we'll have 0, 1, 2, 3, 4. So the key is the value of the node, and then the actual value in this hash map is everything it's connected to. So you have here, we have 1, 2, and 3. You can see from this is an undirected graph, so they're both pointing at each other. At 1, you're connected to 0 and 4. 0 and 4, you can see that and that. At I'm going to switch colors for you. At 2, we're connected to 0, 3, and 4. Oh, I chose red. Yeah. So that's 0, 3, and 4. 3, we have 0 and 2. 2. 4, we have 1 and 2. Cool. And that's evident from sort of the way it looks in the first place. You probably, you'll figure that out after I started doing that, but that's how an adjacency list works. And you'll notice it's not this guy. It's not, oh, I keep switching over to eraser. I don't want that. I'm sorry. It's not this guy, it's this guy, right? It's essentially the same as this thing having this dot nodes, right? So this dot nodes would equal like 1, 2, 3 nodes, would equal 1, 2, 3 if the value was 0, for value equals 0, right? And for 1, that would be 0 and 4. It's kind of the same thing, right? But this might be its own data structure, right? Maybe it's like class adjacency list. And maybe that list is just built on this object that has the actual items laid out like this, and so on and so forth, right? So that's an adjacency list. There's also adjacency matrices, and frankly, I've never been asked them. However, they're super interesting. They're useful from a graph perspective, and I recommend looking them up in the book just to go from there, right? But I've never been asked one. So what I have been asked, though, is to search through a graph and find something in it. And that is where depth first search and breadth first search come into play. And there's a few classes of problems that kind of come up when you're asked about breadth first search and depth first search. For them, I'm going to build a small graph here. All right. Right, here we go. That one looks easy. I'm going to connect these though. Connect that. And then we're going to just connect those as well. Okay, so here is a graph right here. Now to search down it, to say we're looking for the number 7, and let's say the number 7 is here. This is like 1, 8, 9, 5, 11, 1, 12. Let's say that these are the values, and we're searching for the number 7. And we got this wild graph we have to go through. The problem, this is kind of a weird one. This is just to showcase how it might work. Well, there's a few ways you could do it. So you could start at this node, and what is 1 connected to? It's connected to 8 and 9. And one approach, and this is depth first search. Depth first search. That second, that second dash was not necessary. And what this does is this just goes, it takes this, it gets all its children, then it goes down. It just goes down the tree. So it'll go here, 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 and it'll say, okay, couldn't find it. Let's go down the other way. Let's go here, here, here. Oh, we found it now. Here it is, right? Depth first search goes down first. It goes down first. And maybe we're going to keep track of if something's been visited or not. Like, what do we do here? Let's actually pretend these don't exist for the sake of simplicity, right? Actually, it's going to be really helpful to discuss breadth first search with that there. So maybe I should, but actually, no, you can get away without it. But it's a tree like this. I'm going to give it one connection. There we go. Anyway, so that's depth first search. And the algorithm for it is something we will go over soon. Let's talk about what breadth first search is first. So we're going to use yellow here. Breadth first search. And obviously it's in the name, right? Depth, you go deep, you just go straight down first. Breadth, you check out everything that's around you first. I'm actually going to add back, let's do this. Let's do it where these are connected. You'll get the picture anyway. So we're going to start here again. And instead of going down, instead of going straight down, what we're going to do is we are going to go to the left first and the right first. We're going to go through all of the children one has. In fact, let's add one just for fun. There, we're going to check this guy out too. We're going to check out all of these three. And then what are we going to do? Well, then we're going to put each one, when we visit, say, node 8 here, and when we then visit this node and this node, what we're going to do is we're going to add their children to a queue. A queue, that is the data structure we went over just a couple days ago. And this is where it comes up again. In fact, depth first search uses technically a stack, and breadth first search uses a queue. Depth first search can typically be done with recursion, but breadth first search is used with a queue. And if you're ever forgetting how to implement them, start, and you're faced with a breadth first search, start by thinking it's just a queue. You're going to visit each node, queue up their children, and then move on to the next node, queue up those nodes' children, then move on to the next node and queue up those nodes' children, right? So after that, we're going to go visit 5. And when we do, we're going to queue up their children. They have 12, they have 7. We're going to then visit this guy's children. There aren't any, so we're going on to 9. So we're going to look at 11 now, right? And then it's going to queue up its children, which are also 7. Now, here's the thing. You can revisit the same node in breadth first search unless you keep track of if you visited or not. So typically, breadth first search, you have a queue and you have a visit flag. Visit flag, typically a Boolean, right? And maybe you could say something like has, or let's like say is visited, or has been visited. I don't know, the English doesn't make sense there, but essentially there's a flag that says, you could even say visited, I think. That probably makes the most sense, right? Let's call the flag visited. Visited equals false. And then when it gets put on a queue or something, make it true, right? That's how you can solve that problem. So that's how we keep track of it, at least. So now what? Well, the 5 will then we'll visit the children. So we'll visit 12, and then we'll add its children to the queue. There aren't any. And then we'll visit 7, and then we found what we're looking for, and we're done, right? It's going to return there. So that is kind of how that would work out from breadth first search. You're going to go breadth first, and you queue it up in order to pull that off. So let's go ahead and implement these algorithms. Depth first search and breadth first search. I'm going to pull up my screen here. Oh, look at that. It just got some gnarly hair there. Awesome. Let me pulling up Chrome Dev Tools in the background. We're going to share. All right. Out here. Okay. Here is our console. We're up here in the top left. I'm going to shrink that so this is in the center screen for you. Cool. Cool. So what are we going to do? First, we need to create a graph. And to do that, I'm just going to create a bunch of nodes, right? constructor is going to take a value, this dot value equals val, whatever. And then this dot nodes equals an array. Add node val, this dot nodes. All right, let's make a new node first. Equals new node val. This dot nodes dot push new node. And we're gonna return the new node. All right, just in case that makes it easy for them. All right, is that good? Why is it giving me the white text? Interesting. I think it's fine. Okay, cool. So we have add node and we have node. Yeah, I think this is all we need. This is all we need. So let's do a equals new node. I'm going to recreate the graph that I created for y'all. And that one was that's kind of how I recommend it. So when you're practicing these, you're gonna have to come up with your own nodes, your own graphs. So just keep that in mind. Add node 8. So a dot add node 7, that was the middle one. We're gonna add another node 9. And then a at 0, a dot nodes at 0, which one's that? That's the 8 one. We're gonna add node 5. That one's going to, that's fine. All right, a dot node 0, that's all the children for it. The 7 one doesn't get it, so we're gonna go 1, here 0, 1, 2, that's 9. We're gonna add node 11. This is becoming a complicated. A dot node 0 dot nodes 0, that's our 11 node. Dot add node 7, cool. And then we're going to go back to node 0 dot nodes 0, that's our 5 node. We're going to add node 12. We're going to add the node 7, but we can't just add node 7. We have to add the same node. So that's tough. How do we do that? I would say first we need to grab it, and then we need to push it onto this dot nodes for this guy, right? So this guy is our node 5, and we need the one that gave us node 7. That was this guy, I think. So let's check it out. Yep, dot nodes 0. That's the one we're looking for. So we're going to come back here, and we're going to say this dot push. Oh, not that. I mean this dot nodes dot push. And so what does that do for us? Let's check it out. So we're here at 5. Let's check that out first. It'll give us the autocomplete. We're here at 5 dot nodes. And the array we have 0 is 12, and the 7 is the other node, right? And that one, let's get that guy. Nodes dot nodes 1, right? That's 7. Now we made this a directed graph because we don't have it going both ways, and that's totally fine. I'm just doing this for demonstration purposes, right? So whatever, but this is the one that is connected. So how do we figure that out for sure though? Let's do this. We can do a triple equals on this. You'll notice the paths are different, and the answer is true. Why is that? That's because they share a reference, right? Two objects are equal when they share a reference. It's more like, is it the same object, not is it an equal object? It is the exact same object, and that's an important distinction. Because if this were like a deeper object, then anyways, that's just how it works. So that is cool. We've got our directed graph. Now we need to do a depth first search over it. So how do we do that? Function DFS. We start with a node, and I'm going to straight up read from the book. So I believe it's recursive, right? And recursion is something that is weird to folks. So recursion is when you repeatedly call the function again and again, right? You're going to call DFS on node.nodes. I don't know. You're going to next node, right? You're going to depth first search down the next node. We're going to figure out what that next node is, but it's going to call that until there is not a node, right? Or if all the nodes have been visited, right? Because this could actually, it will stop at some point, but we have to be careful. So this is going to be recursive, and the thing with recursive is that you end on a base case, right? That's why this guy exists. This is your base case, and you have to you have to have these here so that it'll stop, right? So if not node, stop, and that'll stop the recursion from happening. Otherwise, it's just going to call DFS next node infinite amount of times, right? Because it has no way of knowing when to stop. So we could do something here like return, right? Return, and there's no node, so just return it, right? So that's cool. What else from there? We're going to, in the book, it says something like visit node, then say node.visited equals true. We're going to work on what this means. I'm just copying out of the book right now. Then it's going to say for nodes dot for each. All right, node.nodes. So now we're going to take all the nodes, and for each of them, we're going to call, we're going to do this. We're going to just say DFS node, right? And that can only happen if node.visited equals false. That's the other way of doing it, right? Or that's the other sort of base case kind of, right? You don't want to search over the things that you've already visited. It's saying we're done. So the thing is, we need a function visit. We need that to do something for us. So what do we want to do on visit? Visit should be, well, we're just trying to see if they work here, right? If they're equal. So let's go back. Our function, instead of visit, what we're going to say is we're looking for DFS node, but we're also looking for, our general search. So we could wrap that, right? Function find node with value. And we're going to wrap that. And so we create this nice little closure. And we can say if node.value, let me erase some of this. If node.value equals value, we're going to return true. Now, the problem is that we need to find a way to make that happen. But when we do reach this, we might actually be inside a different function. And we need this whole thing, this find node with value, to return true, or to rather return with the node, maybe even. So how do we do that? Well, one way we can do that, let found node equals node equals, null. All right, we just keep how it is. Found node equals node. And then we could try to kill it. We could try to say return. Frankly, I don't know if it'll make it the entire thing stop. So that's it. That's an interesting problem, and I wonder why I'm facing it here. And we're going to find out. So you don't need that. We have, for each node, we're going to run DFS on the node, and then at the end we're going to return the found node. Nice. Oh, one big problem. We got to call return. No. DFS node. And the problem is here, we gotta do root value. DFS on the root. There we go. and then return found node. Nice. Okay, that was pretty crazy. But we have our node A, right? So let's take it through it. Find node with value. The root is going to be A. The value is going to be 7. Let's see if this works. Undefined. Great. What messed up there? Let's see if we can't figure out why that didn't work. Well, first, let's console log through all of the node values we're going through. Console.log node.value, right? Here we're going to say, okay, we found it. Console.log found it. We're going to console log the node here, just to make it easier. So we stopped basically immediately. Why is that? Probably, visited is true on it already. A.visited equals false. Oh boy, I wonder if all of its nodes are now visited, right? Let's check that out. Oh, none of them are visited. Perfect. All right. Find node, it does one and then it stops. Why is that? Okay. Let's see, we have node. We set it to true, then node.nodes.forEach. If node.visited, we assign false. Oh no. That's why. If node, you know what? There, saves you the trouble. Okay, so let's do a.visited equals false. All right, now let's do this for real. There we go. We found it 3 times. Oh, isn't that interesting? And we ended up getting the return value, this node here. So we did it, but we found it 3 times. Highly inefficient, right? But that's okay. Honestly, you don't usually, I don't know if you usually use node depth first search well, actually you could. But if it's done recursively, then how do you stop a recursive function? That is hard because it's built up this function call stack. And well, it's just hard to say. Anyways, it found it 3 different times. And the interesting part is that it found it visited it, but it didn't set it to false. It went 1, 8, 5, 12, 7, 7, 9, 11, 7. So that's interesting. So yeah, we're good. I think it found multiple nodes with the value 7. And if I'm not mistaken, there were multiple nodes like that. We had, this first one here. And then if we climb down 9, there's another one there. So interesting. So there were multiple nodes with 7, and it found multiple ones, and it gave us the last one that it found, frankly. I was just one here. That's when you go 9, 11, and 7. So that's depth first search. It's going to go all the way down into the depths. Now, if you remember the graph structure, that's definitely what that should have looked like if that was the case. So breadth first search is done with a queue then. So let's redo this. Find node with value, but use a queue. Use breadth first search rather. And but for a second, I just want to take a second for you to think about how this function was built. And note that in JavaScript, you want to be able to understand closures. And if you don't, go ahead and Google them, right? But I created a closure here. It had this found node. So when I'm dealing with recursive functions, sometimes what I find is I want something out of that recursive function. And one of the best ways to do it is just create a closure. And then when you do that, you just have to remember to call the function inside it, right? DFS, right? And then you're off to the races. So you can run a recursive function inside a non-recursive function. And maybe that'll make things easy for you to deal with. So that could be a really good way for you to handle that. Anyway, so let's do breadth first search. We're going to delete all this. In fact, I don't even know if you need found node, because this is going to be, or find node with value. Yeah, this is going to be, we're just going to call this breadth first search. Breadth first search for value. There we go. So breadth first search just uses a queue. So what does that look like? Well, we take our root. and we get the value. Is the value equal the value? If root.val dot value equals the value, let's just return the root, right? So that's interesting. So we're doing a comparison already. We might need that for the other ones. So why did I do that right there? Well, maybe it was a bad idea. Here's something I like to do, while. So we're going to search through children. We need a queue. Let's establish the queue first, actually. Const queue. It's going to be an array. That's all it is, right? You remember that when we were going over, I was like, oh yeah, queue stacks just arrays. Okay. While queue dot length greater than 0. And what I'm going to do, I'm going to put the root, the very first one. And that way we don't have to do this mess up here, which is stupid. All right. So while the queue length is greater than nothing, while there is something in the queue, let's do what we're doing. We're going to do, how do we do it again? We do queue, let's say let node equals queue dot shift and pop. I think a shift and push were the ones we're looking for. Yeah, shift. Shift. Okay, cool. Queue dot shift. So that's gonna bring it off in a queue-like fashion. That is first in, first out. So shift will take it off the front of the array. And that's going to be our node. And we're going to say queue dot push node dot nodes. What? Well, first, actually, let's do the check. If node dot value equals value, right, then we can return the node. We'll return the node. We'll just back out of there. And this isn't recursive, so it'll just return that for the entire function. Very cool. So we're going to return that node. So what then? We pushed it onto the queue, and now we pushed all its children onto the queue. So now I think we stop. I think we stop. Oh, no. We got to deal with visited first. That's true. Okay. So we gotta mark it somehow. So how do we do that? Well, the thing is, we want to do that to the node that we just did. Visited. Well, this is tough. We need to check somewhere that it's been visited, and that could be a little tough. So we have node equals queue dot shift, and what we want to do is say that the node has been visited. But here's the thing. I think I want to check if it's been added to the queue before. So how should we? It's tough. I don't want the node to be added back to the queue. Let me see how maybe they do it. I think they just mark it. Yeah. If node marked equals false, I just checked the book. Yay. Node marked equals false. Node marked equals true. And then we queue it up. And then we queue it up. We queue it up inside there. Why do we do that? Well, we don't want to re-queue the children of a visited node, right? That would be insane because we've already added its children to it. So then we're like, hey, if node.value equals value, return the node. We do that right after the check, right? And then it keeps going. I think this is it. Oh, no. I don't think this is it. Let's try it. BFS for value A7. Let's see. It doesn't do it, right? I know why. And that's because we messed something up. So let's fix that real quick. So where did that go wrong? I think that went wrong in our There we go. I think that went wrong somewhere in here, right? So we let node equals q.shift. It'll take the root. If the root has not been marked and it hasn't, we're going to mark it, and then we're going to push the nodes onto it. I think what I would rather do is to check each node. Let's see here. I want to bring in the book while the queue isn't empty. Take it off the queue, visit it, and then for each of the nodes, I see. Okay, so let's do this instead. We are going to check the value, but then we're going to say something like this. We're going to say node.nodes.for each node. And we're going to say if node.marked is false, node.marked is true. Then we're going to queue.push node.nodes. Oh, no, just the node. We're going to queue up the node. Yeah, and that should queue up all the node and all their children, right? So that's going to push it on, then we shift it off, and then it's going to go through the entire races. Now, I want to make sure that we got to mark the root somehow. I'm going to do it up here. Root.marked equals true. That's what they do in the book as well. Okay, let's try that out. Oh, what am I doing? I haven't returned a node, but actually it didn't return any node. The value equals 7. Why not? Well, let's check out, let's do some console logs, see what's going on here. Actually, let's see what A is. Marked is true. Let's do A.marked equals false. A, and let's check out its nodes. They're all not marked. Okay, let's see if this will work after getting rid of the marked problem. No, okay. So it's actually not even going through them, which is kind of annoying. Why wouldn't you do that? Queue.push node. Let's see how it goes when we get there. There we go. Or BFS for value. Return values node. I'm going to console log this node. Log the node. Oh my! I did it again. Look at this. Oh my gosh! What is going on with me today? If not, node.marked. Okay, that, I guarantee you that was the problem. Good Lord, there we go. Now we found it. Okay, so that was the first one it could find, right? So I bet it didn't even go through all of them. Let's check it out. Nodes, yep, visited, false, all of them were marked. Let's see what these kids marked. These kids nodes, visited true, not marked, right? On the left side, its nodes, marked as true, its nodes, not marked. So it kind of stopped right there. Interesting. Actually, let's console.log the path. We're gonna change marked to marked 2, just so I don't have to reset the marked status on all these. Console.log node. All right. 1, 8, 7, found it, 7. Yep, found it. Interesting that it still went after finding that first 7. No clue why. So, oh no, that's because it returns the node. So that's just, it went 1, 8, and 7, found 7, boom, returned it, good to go. And this is that same node, right? These two are equal to each other. You can see they're the same. So cool, that's breadth first search. And nice. So when do we use these things? Well, it gives you a few examples in the book, but the number one time we use them is when we're just going down any sort of graph. There are a number of questions that kind of deal with this, and that deal with breadth first search, depth first search. I recommend finding them in the book. I'm not going to do problems today. I'm kind of burnt out. So I'm just going to stick with this, and I'm going to do some other front end prep work. But depth first search, breadth first search, very important. Nail it down, create it, code it out yourself and do it. You're going to get a lot out of it. So thanks for joining today. Sorry, it's a shorter one. I'm still doing it tomorrow. So I'll see you tomorrow.